Thank you, Anatole, and congratulations of your prize. And first, I should thank the organizer of this conference and who gave me a great opportunity to present my studies in this exciting conference. Okay, so my name is Shinya Nishida from NTT Japan, and I'm a vision scientist. I'm not a real VL scientist, but I would like to explain today how the vision science can contribute to the VL technologies. And probably you already know the purpose of the virtual reality, I believe, is how to produce virtual, realistic, perceptual experiences. And the first simple approach is to make a physical input to the user's sensory system close to that of the real experience. This is physics-based, and this is a famous present-optic function picture by Ted Edelson and Bergen. But another approach is, I believe that this has become very popular here. It's a perception-based approach or a perceptual-based approach, and make the response or activation pattern of the user's sensory system or brain or subject perception itself close to that of the real experience. And this is the this is a picture from the same paper by Ted Edelson. And for vision scientists, this paper is mainly about this: how we measure, how the brain measures the plenoctic function. And for the perceptual thing, and probably you well know about the chromatic metamers. Metamer is a very important concept, and it's physically different, but perceptually identical. And in the case of chromatic metamer, it's simple that we have only 3 types of color sensors, and we measure the continuous spectrum by 3 sensors. So the only we can use is the relative activation of the 3 type of cones. But actually, these days, this concept itself is challenged by finding of the new type of photosensors, but I don't go into the detail on these issues. And so this is the hierarchy of the visual system, and from here the sense. So anyway, so from the sensing level to the next. The next level is low-level visual processing, like wavelet analysis in V1. And the next level is then V extra features like a shape, color, motion, and depth. Thanks. Here, and also these features are integrated not only for different property of vision, but also the different modality information, and then we recognize it. And chromatic metamer is only at this level, this level. And we equate the perception, control the perception at this level. And this is an example. This is shown by the Freeman and Simoncelli. And they show, okay, in order to enjoy this demonstration, you have to look at here and don't move your eye. And probably you think that, this picture looks okay. But if you directly look at around here, you notice deformation, messy picture here. But in the periphery, this is, this representation is nearly the metamer. And in this case, you look at here, and in this case, this region it looks okay, and also the other region looks okay in the periphery. And they call this ventral metamer. And this metameric structure is produced mainly at this level. This is a V1 level wavelet analysis plus a V2 level that look at the joint statistics of local features. And so we can do the same games for all the visual system. You can make a metamer at this level, this level, this level, or this level. So that probably the critical concept is the metamer. And if we understand how the visual system represents the world, and we can make a metamer and use it for the VL technologies. And first, I will show 2 examples of that we develop in our lab. And then we explain the other lines of study done in our lab that may possibly contribute to this line of research. The first is the projection mapping thing. And the Spatial augmented reality by light projection become very popular, and for example, in this case, these guys make projection mapping to increase the dynamic range of the stimulus or object, or here the projection mapping is used to control the appearance of the stimulus. And we have a very nice tutorial in the first day of this conference here from my colleagues. And the standard approach, I would say, is the reproduction of physical light transport of pixels, pixel-wise. And I mean that it's a physics-based approach, is the base. But we can apply in a perception base, and this is what we call the deformation lamps or Hengento. And so probably it's better to show the example here. Come here and look at that brick wall.
Yes. Can I touch it?
Can you check it? Yes. Can you check it?
Yes, it's
a real brick wall.
Real
right?
brick wall, yeah.
From now, we would like to demonstrate the effects of Hengento using this wall.
Right.
It's called the Hengento, or Deformation Lamp. How does it work exactly?
Wow, the bricks are moving. Ah! Why are the bricks moving? It's shaking. Wow. Wow, that's incredible.
Okay, that's it.
Wow.
Did you change it?
Yes. It looks like all the bricks are moving as if it's alive.
Yeah, alive, yeah.
But the actual bricks are not moving.
Yeah, it's not moving. It's not. It's just an illusion. So we just do something.
You're right. You tricked my brain.
Yeah.
The Hengento uses a projector to alter our perception.
We would like to explain you a little bit more in detail.
Shinya Nishida shows us how it changes the painting of the Mona Lisa.
She smiled. She's smiling. Oh, and her eyes are moving. Oh, wow, and her hands are shaking now.
Yes.
Yes. How does this work?
Actually, this is a static painting, but by projecting this kind of black and white pattern.
Yes, you can kind of see the eyes moving there.
Yes.
And now her head and hands are shaking.
Yeah, we are projecting different pattern on the top of this.
Oh, very interesting. Her eyes are moving like this.
How can something as simple as light projection create this kind of illusion?
Okay, so technically, this is a very simple technique, and we, just take the picture of the object and then the displacement, the image, following the displacement vectors, and then we make animations, and then take the difference from the original image and that animation and just project it. And this is just a black and white pattern. And so technically, this is not very exciting. But the important point is the perceptual effect. Why it works so well with this kind of simple technique. Actually, this paper is rejected by SIGGRAPH because it's not technically elegant. Although we want to emphasize that it's perception, it's a perceptual thing. That's important. Okay, so this is the difference between the standard conventional like a shader lamps and our technique. And the previous one is mainly physics-based. Now this is illusion-based. And the conventional projection mapping is to try to replace everything by the projected pattern or to erase the original pattern. But here we try to keep the reality of the object. For example, in a wall looks like as it is, and just add the motion to it. So that it's a kind of a merge of the real reality with the virtual reality. So that's a new type, I would say. And the other important point is that the previous attempt to make a physics-based approach, you have to turn off the light. For example, if we do it in the SIGGRAPH E-text, they make the room very dark. In the most demonstration, they want to make everything dark. But in our technique, even in the light, the normal bright situation, of course, not under the strong sunlight, but in the normal situation, it works well, reasonably well. So that because this is based on illusion, we don't need to reproduce everything. So the basic structure here is that our visual system basically analyze color, form, and motion separately in the brain, and then combine it together. And our technique try to do is to just change the motion system, just cheat the motion mechanism, and later in the brain it try to integrate everything, And even if there is some inconsistency in the brain, just think it's okay and just combine it, so that we see it okay. Okay, let's do it more in detail. Okay, first, how we detect motion, and this is a famous picture made by Ted Ellison. And this, okay, if the line is moving to the left, and if you write it in the space-time domain, it is a diagonal line. And if we show it in the Fourier domain, this is a line. And this is a gradient drifting to the left, and this is in a space-time domain, it is an oriented line. So the motion detectors we have is like this, and this is in a space-time domain. It's a nearly the linear filter detecting the local orientation, local slanted signal in the image. And also this is supported by physiological studies. And here only look at here, and this is space and time plot of the resonant field of V1 neurons. And these neurons shows a diagonal, a slanted resonant field in the space-time domain that can detect motion. And so that in order to make the impression of motion, only we need to do is just activate this detector. So that this is a famous demonstration originally made by Antis and Rogers. And this is the 4-stroke apparent motion. And actually, this image made of only 4 frames. And originally, it's just 2 frames. And first frame, and so first frame here, and then shift it to the right, and then reverse the contrast, and then backwards and forward contrast. And this is just a repetition of these 4 frames. And why this works? Because this activates the motion detector we have in the brain, so that this is sufficient to do it. So that and also an important point is that we can separate the input into the color signals. This is L minus M, and this is S minus L plus M, and this is a luminance channel. And mainly, motion system. Ordinarily, it is suggested that the motion system is colorblind, but it's too emphasized thing. But mainly, we are more sensitive to the color luminance signal for motion perception. So that in order to drive motion system, you don't only drive the luminance signal. And another important point is that then what happened for color? Okay, please stare here. Don't move your eye. Don't just look here. And here we show the color patch, and this color patch never move. But when I move the background, dot, probably I hope you should see the illusion of the movement of the color together with the luminance signal. So this is called the motion capture. So that since the visual system is not, motion system is not sensitive to color, the strategy visual system takes is to rely on the luminance signal to estimate the motion of the color. So that if we drive the motion luminance signal, luminous motion, then it can capture the color of motion. And also the motion affects the position and orientation. And here probably you have a gobble patches, but once I move it, you see a clear change of the position, and this is far separated than this. But physically, this is the same. This is there is no they are the same. Just I move it. And also and here And the next demonstration is look at here. Just look at here. Don't move your eyes, and we will induce a motion after effect. And probably in a few seconds, it stopped. And I hope you to see the backward motion. But the important point is that this illusory motion actually changed the orientation of the pattern. I mean that this illusory signal is purely motion signal that can change our form perception. So that means that if you just change the motion system, that can affect the position and the form information. And this is an example that, here, sorry. So, it's hard to see this letter, but when I move it, you see it much easier. And this is kind of display indicates that we use motion information to integrate form information. So this is an example that how the motion affects form perception. And motion also affects color. And in this demonstration, I moved the bars, the bars color is red and green, red and green, and moving. And it never, if you fixate somewhere, it doesn't, mix on your retina. But perceptually, you see color yellow. So that this supports that, if there's a motion, we integrate color information and form information together to see the consistent world. So that the only controlling motion is sufficient to, see the realistic image. For example, in this case, here I moved everything, both luminance and color, and you see okay. And here I just changed the luminance, the pattern, the form, the luminance pattern. But still it looks okay. So that just changing the luminance is sufficient to make the whole thing, color and form. And so that this is the technical points of deformation lamps, and it do not correctly reproduce target movie on the object surface at only dynamic luminance component. And it effectively drives human motion detectors, and the luminance motion captures motion, color, motion and texture, making small dissociation invisible. And another thing I want to emphasize is that in a bright room, luminance contrast of the project image can be smaller. But it's okay because it's just make the apparent displacement smaller. But it's okay because our intention is not to reproduce something correctly. Only we give us an impression of motion, and even under that situation, we see perfect motion here. So, for example, this is the case that we project deformation luminance pattern to this image, and then you see deformation of the pattern here. But one problem is the size of deformation. If you make it too big, probably you see dissociation of the project pattern and the original pattern. And in order to solve the problem, my young colleague, Taiki Fukiage, has developed a new automatic motion magnitude adjustment method using perceptual model. In his, and we will present it in this demonstration in the 12th floor and also in a paper session this Wednesday. And the point is that, if the input vectors, or what we try to make it too big, we need to reduce it. But how much we should reduce it depends on the perceptual system. We need to know how the visual system works. So that he implement adaptive retargeting by implementing a perceptual model. And he make a perceptual model mainly based on the V1 level. And then they predict how much the motion vector is tolerable or acceptable for the visual system to see. And then this system automatically adjusts the magnitude of the motion vector projected. And please look at this demo after my talk. Okay. So the important point is that this technique includes the perceptual model. So the visual science, knowledge of visual science should be implemented here, and then we can make a very, very elegant VR technologies. And also we applied a similar idea to the stereo thing. And for example, we can project the left and the right image like this inducer pattern, the black and white pattern, to this projector, and then see that people with glasses can see 3D, and the people without glasses can see the original pattern. And from this idea, we have developed this new technologies to make a stereo that is perfectly 2D, 3D compatible, which we call the hidden stereo. And in this method, if we have an original central image, and then we make an inducer image, and this disparity inducer image is added to the, is it added? Yes, to this image to make the left image. And this image is subtracted from this image to make the right image. So as a result, if these two images are presented on the stereo display and look at the result glasses, you see it normal original pattern. But with glasses, you see these two patterns separated to the left and right EI. And if they make a perfect stereo, it's okay. And so the logic is how to make this inducer pattern. And here we make a little bit more elegant way than what we use in the projection mapping here. And this is the original pattern. Okay, assume that this is the sine wave grading, a luminance profile of the pattern. And basically, added pattern is a quadrature phase of this pattern, or the derivative of this pattern. And then add this one, is shift the phase of this pattern to the right, and subtract it, then you shift in the opposite direction. And here you have this disparity here. And if you want to control this magnitude, then we just change the magnitude of this component, right? And then this is the basic logic. And you can do the same thing for the old spatial frequency and the old orientation. Just do the same thing for everything. And here so this is for one spatial frequency, and this is a higher spatial frequency, and you can shift. In order to make a same magnitude shift, you have a stronger signal. You have to increase the magnitude of the signal, this quadrature phase component. And obviously there is a problem, because if this pattern is too high spatial frequency is too high, the magnitude you need to add is beyond the limit of the display, or there's a big magnitude. But so that we just cut, we just add the limit to the magnitude we add. So as a result, what happens is that there is an inconsistency between the magnitude of depths, in disparity between different spatial frequency. However, we believe this is okay. One reason is that we are not very sensitive to the higher spatial frequency when we see the disparity. And another reason is that our disparity processing is like motion. It's like we have multiple channels for it, and see it in low spatial frequency, high spatial frequency, and low high spatial frequency, and then we integrate depths so that even if there is some inconsistency, we can ignore it. And so this is like motion energy model. This is the disparity energy model, and this model predict that only look at the phase. The important point is that this is mainly for detecting the phase of a frequency component, so that our technique try to drive these detectors, so that we don't need to, we don't intend to reproduce a correct image on the left and right. We just try to cheat the binocular visual system to behave as if it received the standard input. And this is an example. I don't know how many of you can see the image. And this is for the cross fusor, and you cross you look at this to the right image and left image, or for parallel fusion you see here. And this is a standard stereo case. And I hope you can see the little difference, but I know that it's hard. So just simulate it as a motion. And this is a left image, and this is a right image. And as you can see, you see a kind of motion paradox here. And there is a little difference you can see between the hidden stereo case and the standard stereo case. But what the critical difference between these two is when we merge or integrate, or just sum up the left and right images. And here, this is a standard one, and this is a hidden stereo case. And if you close up here, there's a bunch of blur here for standard stereo. But in our case, there's no blur. Actually, our subject couldn't see any, artifact here. But the problem is that our technique cannot produce a big disparity. But within some range, this the perceptual quality of the 3D is nearly as same as the original 3D stereo. So this is the hidden stereo summary, and the hidden stereo enables ghost-free viewing for viewers without stereo glasses, and the hidden stereo can effectively produce depth when disparity size is not very large, and at least up to 6 minutes. And the hidden stereo is a perception-based, physically incorrect method, but it works well. So the important point is that since we know how the visual system works, we can imagine how to make it cheated. Even though it's not correct, we believe that it's okay because the visual system should work in this way. So that the knowledge of the visual system helps to develop something that is impossible, because the 2D, 3D compatible display is, many techniques, have been developed. It's use a special hardware or something very complicated way. But here, we just use the standard display. We need to just change the data. And we can actually demonstrate this with the standard home 3D TV. And in the home TV, in the home, the problem is that without glasses, we don't have a sufficient number of glasses for each family, so that we know that it's not good for the young children, so that we should avoid, we normally avoid using 3D. But this system is okay because it's perfectly compatible. Even in a movie theater like this, either with or without glasses, you can choose whether you see 3D or 2D. Okay, so that's something we already apply to the VR technology. But from now on, I would like to explain some other stuff that may be possibly help to develop the new technology in the VR from my list of studies. And one is the cross-modal timing judgment. First, and this is not my illusion that I found. This is originally found by Motusis and Zeki. And they found that cross-modal, in this case, the judgment between the color and the motion that are considered to be processed separately in the brain. And the interesting thing is that if you, okay, I would like to hear. Now you see red and green, and now it is up and down. And my question is whether the motion is, when the stimulus is moving downward, whether the color is red or green. Okay? So how many of you think it's red? How many of you think it's green? Okay, so, but you should look at here. There's an answer here. Actually, this is, the direction of motion is downward when the color is red. But, this is, a very strong illusion, and probably the 50%, even though trained people cannot see it properly, and it is, it's a 50% chance. They cannot correctly match the color and the motion direction. And so the interesting point is that here, I think now you think it's easier to judge that the motion is red when it's going down, But there, in this case, there's a time shift. And actually, the motion changes a little bit earlier than color. And in this case, the subject can correctly match the color and the motion. And what this means? And originally, the Motosis and Zeki proposed that this indicates the processing time difference of the color and the motion. And many people still want to believe in that way. But this is very strange because there is a 100 millisecond delay we need to explain. And also, in this case, we should assume that the motion processing should be slower than color. And this is physiologically implausible. And also, if you measure the reaction time of the stimulus, we cannot find any difference. So that this is just a subjective illusion. And so we proposed the theory that we call the time marker theory. And important point is that in order to compare the timing of two events, we cannot directly access all the signals in the color and the motion. So we see color here, we see motion here, but we cannot directly compare everything. So in order to compare, you need something to share between two representations, something like saliency or a marking point. And this illusion is mainly coming from the mistake of assigning proper time marker for the onset of motion. Onset of motion is not easy to detect because motion is already the temporal change, and this is the temporal change of the temporal change. I mean, this is like a peak of stock market. It's very hard to predict when the peak is. It's easy to say that when there's a change here. But if there's a trend and if there is a downward trend in the noisy situation, it's become very hard. It's a second order derivative. So that this theory can predict why we see the illusion here. But what I just want to say is that cross-modal timing judgment is very inaccurate. And another example here, and here the matching, your task is to judge color red, and this is orientation here. And the subject has to tell whether the color, the orientation is this way or that way when the color is red or green. Do you get it? So this is the binding task. This is something similar to that I showed last time. Okay, let's do it again. Okay, obviously in this case, the orientation is this way when the patch is green here. And probably at this slow rate, you can judge it. And the question is how fast we can judge this relationship. And this is 1 Hertz. Still, you can do it, but the 2 Hertz, it's nearly impossible. And at the 4 Hertz, no one can do it. I don't know anyone who can do this task at the 4 Hertz. And this is not only about orientation and color, but also for this is sound and the color binding thing. And so yeah, in 4 Hertz, probably no one can do it. So the important point is that you can see color change. You can hear the sound, but you cannot bind it together. So that a perception of each modality is different from the perception of binding thing. And the binding system is slow and attentive. And another example to show that it's attentive is that, okay, so your task is to tell which one is flickering in synchrony with the sound. I think it's very, very difficult, right? But the interesting thing is that if you know so the first, okay, so please attend here. Easy to judge, right? Next one is here. So it's quite easy. And here, the next one here. So this is not the limitation of the binding itself. This is an attention thing. In order to pay attention, you don't have a rich source of binding information across different channels. This is very important when you consider the multimodal integration. You cannot evaluate the performance of binding or multimodal sensory thing, not at each one. And this is the attention thing. Okay, and the other example is the timing judgment is adaptive. And here the sound source and this is the audio-visual timing judgment. And here you see the flash here, and you see the auditory sound here. And the task of the subject to tell whether the data occurred at the same time or not. And if there is a delay of, for example, 100 milliseconds, the people say, okay, yeah, there's some delay here, right? So it's possible. But after adaptation to the delay of 300 milliseconds, for example, and for 3 minutes, and then return to the original condition, and then people say, oh, I cannot tell. It's nearly C at the simultaneous. So that the point of simultaneity is adjusted. Just like a visual motor thing. In a visual motor thing, you can adapt to this time delay. But in a sensory domain, you can also adapt to this thing. So that we don't have an absolute clock. A visual system or a sensory system try to learn the synchrony of the multi-levels input from the correlation in the world. And if there is a correlation in the world, we use, and estimate the delay, and we can estimate how much delay there should be, and just compensate for it. Always our system is adapted. So I think this knowledge should help to understand, to use the multimodal information in the VR technologies. And another thing is material perception, and this is one of my main topics these days. And what in material perception is, we normally call it shitsukan in Japanese. And shitsukan is a translation of the shitsukan in the sense of quality. And we said that shitsukan is the decoding of object natures by brain. And this is the physical, like a physical glossy, like glossiness, or the material, what it is made of, or what kind of condition they are, or what kind of emotional value you think it's yummy or something. These are everything is shitsukan. And the question is how we estimate this, how we get shitsukan from the image or the other modality, including a tactile, haptic sense. And so we are running a project. And first, we start with the project called Brain and Information Science on Shitsukan from the 2010. And then this is in Japanese called the Shitsukan no Jouhou Gaku. And then after end of this project, we integrate more the computer graphics, haptic engineering, and digital fabrication, as well as the data mining of the machine learning, brain decoding technologies. And we are now running against Kanchi, or the innovative Shitsukan science and technology. This is a big Japanese project, and many of the members join this conference as well. And my starting point of my interest on this material perception is that when I first watched this kind of movies in a very early, in the at the end of the last century, and this looks very realistic. Although from the current point of view, this is not sufficient enough, good enough, but still it looks okay. And but as a visual scientist, we wonder why this looks okay. We have no answer for it. So that we want to understand why we can see the computer graphics people only try to physically simulate the world. But from the perception scientists, we wonder why this looks naturalistic. And if because this is a hard problem, because as you all well know, the image is made of a three components: lighting, geometry, and material. And combining, and in a complicated interaction, this image is made. And in particular, this, the surface reflectance is probably people believe that it's related to the material perception. And BLDF is very, very complicated, and many parameters. And also the BSS and RDF, or many, physically, if you really want to measure it properly, you need a terabyte kind of data to describe it, so that how the visual system handle those problems. And so, for example, here, this is a very simple demonstration of a CG, and this is a shape and no reflectance, no manipulation of BLDF. Everything is a Lambertian. And here you see, everything is, more like a classical CG kind of thing, and no material, no sense of material here. So that, so they're probably using, why don't you add the make a BLDF more complicated? But it doesn't work very well. Even when we make it more glossier or something, it doesn't look realistic too much. And as you well know, the critical factor is illumination. And this global illumination helps you to see the world very, very realistic. So that means that in order to explain this visual perception, the visual system has to take into account not only the reflectance, but also the illumination of everything. But then the problem becomes really, really complicated, because the image is made of generated by geometry, material, lighting, and inverse optics thing. This inverse if you can estimate this parameter from the single image, that's okay. But it's terribly difficult, because the BLDF is very, very complicated, And illumination itself is really complicated. So the illumination of me here in this room is everything here. So that the visual system cannot estimate everything here. So it is seriously ill-posed problem. So the question is whether the human system seriously solves inverse problem of immaterial perception, and probably not. And so this is, for example, the example. And here the D2 images are rendered with the same surface reflectance parameters, but the shape is different. And then you don't see it with the same material, right? So that this means that we don't have a material constancy against shape change. And for illumination change, and this is work done by the Roland Fleming group and Ted Edelson's group, and they show that as long as the illumination is natural, if you change the illumination, it looks okay. But if the illumination is unnatural, then you don't see it very well. This looks different. So in the same demonstration, this is the natural illumination image, and here the different illumination. And the interesting thing is that you see the big difference in the local image. Image is totally different, but the sense of material is very similar. So that means that we can extract something, abstract sense of material from this complicated situation. But if the illumination is like a snow world and in a ski resort, you don't see it realistic. So that the critical point is probably the image statistics here. And for example, here, assuming that this, this sphere, and this is metallic, polished metallic, and you see it's clear image of the world. But if I blur it and then just cut it, and then you now see it more blurry kind of surface, you see the clear change in material here. So you don't need to know the exact pattern that is reflected. Only you need to know is the image statistics difference from this and this. And from this, we know that, we estimate that it is not the world that is blurred, but it is a surface reflectance that blur the world. And in order to conclude that this is blurred, we know that every world is not blurred, right? So normally the object has a very sharp edge in the natural environment. So that we use the knowledge about the natural image statistics. So that this is the standard visual, the inverse optics approach, and the physics variables and image variables, and this is a forward optics and inverse optics. But we just relax it to the more just a statistical correlation kind of idea, and just use the statistical correlations as a way to estimate the material. And this is one example we propose, and with the Ted Edelson's group. And here the gloss perception, and critical information about gloss lies in the luminance histogram information. And if you look at the luminance histogram, this is glossy image has a more positively skewed compared to the matte image. And actually, if you just change the manipulate the luminance histogram to have a more positively skewed, you see it glossy, and here you see more matte. But many people complain that this framework is too simple because we know that the gross perception includes the shape information as well, and so that we analyze the image, and we noticed that the critical point is that histogram matching technique actually changes material but not affects shape information. So I mean that you see similar shape although you manipulate luminance histogram. So then so that the important point is that the histogram equation doesn't violate the intensity order information. So we show that the material change doesn't affect the luminance order information so much. So that from this psychophysical experiment, we show that people are okay to see the same shape as long as we keep the luminance order information. I mean which one is brighter than the other. As long as we keep the order information, we see the same shape, but the material appearance changes. But once we change the luminance order, we see different shape. So the shape and the material look at the different aspect. And this is the current model. And we look at the magnitude, gradient magnitude information and the gradient order information. The order information is used mainly for shape, and the magnitude information is used mainly for material perception. And we extend this kind of this line of study to, for example, wetness perception. And here, I think you see the image looks more wet, wet. From left to dry, wet, dry, wet. And the critical manipulation here is that first we make luminance histogram a little bit more positively skewed to make it more glossy and dark. But the other important point is to make color saturation higher, and it becomes more colorful. So if you make it more colorful, you see it's more wet. So the reason, and actually this image manipulation makes most of the image into more wet. And this is the physical analysis of the image. And actually what happens is that if the surface is wet, the light coming from the outside interacted with the material more often than, it goes more into the deep of the surface, and it interacts with the surface, and that results in the sharpening of the spectrum. And this is the reason. And also we found that there are some image that is effective for this manipulation, and other image that is not affected by this manipulation. And the critical parameter is the hue entropy. And the number of the colors included in the image is critical, because the visual system has to estimate whether that color change is coming from the wetness or some other factors. And if the same change occurs at the same time in the image, we more reliably estimate that it is mainly coming from wetness. And also, this is another example of the sub-resolution, another example. And here, this is a hair. And this hair is rendered with a width of 1 pixel, and this picture is rendered with a pixel size width of 0.3 pixel. And probably you looks finer. But this is finer than the sub-resolution, So in this manipulation, and important point is the critical parameters to see this manipulation is that here there is no line image change width. Image with line width is the same, but the U looks finer and finer here. What is changing here is actually this is a power spectrum analysis, but the important point is the luminance contrast. And if you just change the luminance contrast, then it looks finer, because it is due to the central limit theorem, and you sample more and more stimulus. The mean doesn't change, but the variance is reduced, so that you see it more finer. Visual system knows this rule. And this is an example. Probably you see it glass. Now this one looks more like the rubber thing. So the visual input is the same, but the cross-modal, the auditory input helps. But the auditory sound itself is not sufficient. The visual system is not sufficient. So that what visual sensory system try to do is to do the maximum estimation from the two resources, and just look at the product of the likelihood. This is our data can be explained by this framework. And this is another example of a liquid viscosity. And probably you see liquid only from motion. And we make motion flow from these movies. And you see, I hope you see and in this example, you see the liquid viscosity is higher here and lower here, but we just change the luminance speed, local motion speed. So this is a demonstration that local speed is critical. And okay, so I skip this. And this is another example that here the deformation, dynamic deformation, give you an impression that you see the transparent layer in front. So that as long as it doesn't move, you don't see any surface. But with dynamic deformation, you see surface. So this is a new type of perceptual transparency. And we analyzed what kind of deformation is sufficient to give an impression of a liquid. And this is a very simple bandpass filtered version of the image that gives us a reasonable sense of liquid here. Okay, so this is a summary of the kind of features, the material sense, and its image features. Okay, this is a concluding remarks. And perception-based VR technology can go beyond the limits of physics-based method. And important point, they use metamers at multiple stages of sensory processing, not at the peripheral first level, but all the stages you can apply this technique, and that will help you. And in order to use that, probably the real scientists or engineers should learn more about vision science. But I think this is very hard thing because you are very busy. So that I think the vision sciences should integrate our knowledge, achieve knowledge into such model that can predict metamers at multiple stages of sensory processing. And so that I think that we need to make a model that can easy for the engineers or VR scientists to use and make this kind of technology. Thank you.
So we have time for some questions. Feel free to go to the microphones which are located in the room and ask questions to Dr. Nishida. And please, if you could just identify yourself before, that would be great.
Hi, my name is Tobias Langens from University of Otago. Thank you very much for the great talk. I have one question. When we take your perception-based approach, we as technologists, we think we would like to apply these technologies and also perception-based approaches more. But do you see any long-term effects? Do you think this illusion that you try to introduce will break after some time because I'm constantly exposed to them? So for example, some of your illusions are not just based on the distribution of rod or cones, but really of our processing in the brains, which we might change.
Okay, so for example, in particular, the cross-modal effects are mainly based on your learning or experience. For example, if you relate that specific image feature with some taste or something, that is easily, reorganized. But after exposure to the virtual reality environment, people just forget about it. So that there is something that you learn if you learn it, it can be updated by the virtual experiments. But if it is more, a basic thing, like a stereopsis thing, or I hope that those cases, probably it's more robust. So that depending on how much, that effects relies on the experience. In particular for cross-modal thing, I think is easily affected by training or experience.
Thank you.
Hi, this is Gudrun Klinke from Technical University Munich. This is a really inspiring talk, and I agree with your last bullet. Please tell us more about this. Though metamers are something that are depending on and different for different people, like colorblind people have different metamers than others. How sensitive are your techniques to the differences in human sensing systems?
It's really a great question. And as for the color, we know the genetic reason of that metamers are different. And for stereo, for example, I believe that probably that is also affected by how much the weight of the different spatial frequency or the sensitivity or many parameters are different. So I think that if we at this stage we cannot say it, but it's perfectly right that if we introduce a new metamer technologies, we need to evaluate the individual differences and how to predict it, and that would be the very important thing. Thank you very much.
I'm Benon Bastani from Facebook Oculus. The question I have is, so these are great ideas, but the full integration into the system, the GPUs and CPUs, especially on the mobile processor, it's very hard to take advantage of these features. The way they're designed, right? And any thoughts like how you propose maybe the existing pipeline are you proposing a new silicon and new processing, or are you saying, well, there's tricks you can play and maybe don't do binning, don't do resolve, don't do any thoughts how you would actually integrate it into the actual systems?
Okay, so my idea is quite preliminary at this stage, and I'm just impressed by the recent the finding of, for example, deep learning network trained for the object recognition have a cortical structure, layer structure, representation is quite similar to the brain. So that I would like to make something really basic thing. But of course, I also heard the talk yesterday that the people want to make a pipeline for the early level modeling, like a lens or something. And also the Brian Wandel group is trying to make a realistic model. So that I think, all the model, like in particular peripheral model, can be made many realistic one, and we can integrate that knowledge. But here my emphasis is more on the higher level. More cortical level processing. And this is still more vague. So that for that stage, probably I think a deep learning would help us to make more realistic. And the cortical decoding technique would be very helpful to check whether the specific image metamer in some cortical level or not.
Thank you.
Any other question from the audience?
Good morning. My name is Svetlana Bialkova, Utrecht University. Great talk, I enjoyed very much. Thanks. But I would like to ask, do you have explanation? Now you mentioned at cortical level, just an example, how do you explain the illusion that people perceive in a different way shapes when you change illumination? Do you have explanation? Because now you've shown very nice fact, but you've been talking about cheating the system. Do you have explanation on the brain level, on perceptual level, deeper?
So are you talking something about dress effect or?
Just an example with how do we perceive a different shape when you change illumination.
Illumination, okay.
This is an example, but
okay.
you've shown a lot of examples, so we don't have time to go into details.
Yeah. So that as for your specific question about the stability of the shape, I think our argument is that the luminance order information is important in the image, so that if the illumination change the luminance order, that can, or the orientation structure of the image. So visual system has to estimate the shape from the image features. So that if the illumination doesn't affect that feature, that's okay. But some illuminations, that violates or change those local features. So that I think that that kind of modeling is important to explain the stability of a constancy of the shape perception, color perception, and a variety of features.
But would it be a temporal or a special approach or a component? Have you already looked at this direction on a brain level, on a higher level integration of different modalities? Because this is slightly related to the question from Facebook. If you want to build a future model, you have to first understand the mechanisms underlying all these nice illusions that you've shown to us.
I understand that I'm still in a very preliminary stage, and I think today I would like to encourage young researchers this direction of research and the combination of the vision science and the VR technologies. And I cannot solve everything by myself, but I really understand that there is a big gap between that concept and the actual application of the study. So I really want to discuss with you more and what we should.
Definitely, I've been very inspired, but then the questions.
Yeah. So that if everyone have that idea, then let's consider what to do next.
Yeah, very inspirational.
Thank you very much.
And the last question.
Okay, thanks. Hi, I'm Project from Roskilde University in Denmark. It was a very inspiring talk, partly also because, like you, I'm new to VR and more like a cognitive scientist and basic research person. My question is, do you have any brief comments about effects of like cross-modal effects, especially in terms of, especially subliminal effects on, say, action system when you change object properties in the visual, so like for instance, perceiving affordances of different objects?
So probably I need to be more careful to answer your question, and it's very difficult questions. And I'm not working hard on that affordance thing and action thing, but I believe the similar approach can be made in a way, but I would like to discuss it more with you. Yeah, thanks very much.
Thank you.
So the next session is at 10:15, Kiyoshi? 10:15 the next session, so you can get a brief, fast coffee. And before that, let's thank the speaker again for his presentation.